Similar right triangles is on our agenda today. We have something pretty interesting here that you have to, I just want you to pay attention to this first part. You don't have to write anything down. I just want you to pay attention and understand what's going on. If you want to jot a few notes on this first part, you can, but I don't need you to write everything down here. I just want you to pay attention and understand. So we have, let's say we have this right triangle. It's right triangle ABC. Now what I want to do is I want to drop a perpendicular, or I want to make the altitude. Let's use that word. That's some vocabulary we use. I want to make the altitude here from this vertex to the hypotenuse. All right, so let's look at some of that. Ooh, what's the screen doing? Oh, there we go. So that's what we have. And so looking there, we have, there we go, we're back. So we have the large triangle, ABC. We have two smaller triangles. We have BCD, and then on the left there we have ACD. Now, what's the relationship between these three triangles? Well, let's look. I'm going to split them up to look like this. Okay, what's the relationship between those three triangles? Well, we're looking at these three triangles split up. I have them labeled here. We should know, remember that this was a right angle there, and this was a right angle. This triangle has been rotated for you. So, rotated so that way they all are pointing in the same direction. You see, it used to look like this, and I pointed them all in the same direction. Now I want to look at these two. Okay, I just want to look at these two. What are some things that we know about these two triangles? Well, that right angle, right? This one was a right angle too. What do you know about right angles? Well, all right angles are congruent, so therefore we have one angle that's congruent. Do you see anything else there that might be congruent? See anything else that might be congruent? We have CD. CD's here. CD is not down here in the big one. Oh, how about this? Angle A, angle A. Congruent angles it seems like when you guys split things apart, when you split these two, this orange triangle out of the larger triangle, you tend to forget that those two angles are the same exact angle. Because remember, this one will sit down right there like that. And so that way that angle A would match the other angle A. And so now, what can you tell me about those two triangles? Well, you can tell me triangle ACD is similar to triangle ABC. That's a similarity statement. And so since they're similar, you also know that that angle is congruent to that angle there. You know that side BC is proportional. BC over CD is proportional to AC over AD. So therefore, you know a lot of the stuff there. Just by drawing an altitude, and then looking at this smaller triangle compared to the large triangle. All right, so that would be those two triangles. Now let's look at this one. Let's look at these two triangles. What do you know here? Well, right angles are congruent, right? And you also know this angle B happens to be this angle B And so, once again, you know that triangle ABC is similar to triangle, let's see, ABC, CBD. So therefore, you know those two triangles are similar. And therefore, that angle must be congruent, sides must be proportional. Why are these two triangles similar? Before we had this in there and this in there. Why? Angle, angle. Angle, angle made those two triangles similar. All right. So now, we have always been working with this large triangle, the original triangle we started out with. Now, on the next slide, we're looking at both of the triangles that came from the large triangle. Of course, right angles are congruent. Is there anything else? Well, we know CD is congruent to CD. Reflexive property makes that true. Okay, now this last part here, this might be a little bit tricky for you to see. So that's why I'm bringing back, here we go, I'm bringing back Papa Triangle here. All right, so if we look here, Papa Triangle and little triangle here. It wouldn't be little triangle, it would be medium triangle. They're going to go take a little walk here. Let's look up here at the red triangle, the pink triangle. We do know that if we allow this to be x, that angle to be x, and this angle here to be y, we do know that x plus y must equal what? Well, if this is a 90-degree angle, x plus y must equal 90 degrees, because the three interior angles of a triangle should add up to equal 90 degrees. Okay, so x is right here, y would be down here. Now what I want you to think about here is that, do you see that this angle right here is 90 degrees? And so if that is 90 degrees, what do you want to call this angle ACD? What do you want to call angle ACD? How about the measure of angle ACD plus x is equal to what? So what did this angle here and angle x add up to equal? They add up to equal 90 degrees. It's pretty interesting there. Because why is that interesting? They add up to equal 90 degrees because this is a right angle. X plus this angle is 90 degrees. Okay, let me get rid of some of that stuff there. That way we can have some room to look at some stuff. All right, well, going back to what you've learned from algebra, I want to get this by itself, that unknown by itself. So let's subtract x from both sides. So we're going to have the measure of angle ACD is equal to 90 degrees minus, I guess we could say that that was x degrees, right? Okay. Now, what about over here? What about if I want to get y by itself? Well, subtract x from both sides. And so now we're left with y is equal to 90 degrees minus x degrees. And at that point, there should be something going off in your head there. 90 minus x, 90 minus x. So, do you see how 90 minus x is equal to 90 minus x? So therefore, The measure of ACD must be equal to that. The measure of angle ACD must also equal y, because both of them equal 90 minus x degrees. All right, so let me erase some of this. I'm going to leave that last part up there. So if we look here, the measure of ACD, that would be right here, that's also equal to y degrees. I guess I could probably put degrees here. We had a 90-degree angle, and we said CD was congruent to CD. Well, you might be thinking side angles, or you might be thinking angle side angle, similarity postulate, but remember that's not a similarity postulate, that's a congruence. It's congruence for proving those two triangles to be congruent. So what we have here, though, is we have one angle, and we have, of course, another angle that is congruent. So therefore, those two triangles, triangle ACD, is similar to triangle CBD because of the angle-angle similarity postulate. Kind of interesting. And so from here, now that you know, going back to what we had at the very beginning, now that you know that all three of these triangles are similar, then of course you can figure out which angles are similar. You can find some missing measurements and things like that. Well, that's what we're going to be working with. We've just proven this theorem right here. I'll give you a moment to read it. The two triangles are similar to the original and each other. So on all those slides, that's what I've proven to you, is that the two triangles were similar to the original. We did that first, and then similar to each other. We did that last. That was the 90 minus x. So therefore, this theorem here is going to be mighty helpful if you come across this on, say, a standardized test. Okay, well, let's look here. Find the value of x. Well, we know two parts of a small triangle, right? We know 5, and it might even be helpful for you to draw 5, here's the 90, and then x is that part. The hypotenuse is right there, but we don't know the value of the hypotenuse, and we're probably not going to be working with the hypotenuse. And 13, okay, this is a triangle that's a little larger, and that's, you know, this triangle here. So now we have, okay, 13 is the bottom. No, 13 is not the bottom. If I were to take that one, this triangle here, and turn it sideways to stand it up, kind of like I've done here, 13 now becomes this part, and x is the bottom. That's what I was meaning by the bottom. There we go. You see how that works? And so now, because the last theorem that we've just proven, that we just looked at, yeah, well, now we can set up some ratios. All right, this is the part where I want you to start writing. Take down these notes and then start writing from here. Find the value of x. So therefore, let's just go ahead and say left side of small triangle over top of left side of large triangle. That's equal to, now since x with the small triangle and it's on top, 5 has to be with the small triangle, so it's going to stay on top. That's the bottom of the small triangle, and this x is the bottom of the large triangle. And so from here, it's just cross multiplying. X times x will give you x squared, and 13 times 5, 13 times 5 will give you, what is that, 50? 65? X squared is equal to 65. Take the square root of both sides. So x is equal to, remember we took the square root of both sides, so it's positive or negative, square root of 65. And since we're talking about a value, a tangible value here, we cannot have the negative value. So we need to be looking, can we say the square root of 65 is simplified? 4 does not go into it. 9, I'm checking perfect squares. 9 does not go into it. 16, 25, 36, 49. The next one would be 64, and the next one's too large. None of those go into 65. But I can also tell you, going back to what we started with right here, 13 and 5 were both prime numbers. You couldn't pull out a perfect square out of 13. Or you couldn't factor 13 and 5 to get a simplified radical here. So x is equal to the square root of 65. This next one I would like you to try on your own. It's basically the same problem, just different numbers. So you try it on your own, and then hit play when you're ready to go. I'm looking at a small triangle, and then I'm looking at a larger triangle. Small triangle has 3 and B. Large triangle. Okay, so this one is going to have to go this way. 8 is this part, and B is this part. So let's set up our ratio. B over 8, and the other one, the other ratio, the bottoms of the triangles. 3 over B. That leaves us B times B is B squared, and 8 times 3 is 24. Now remember, there is a perfect square that goes into 8, so when we take the square root of both sides, B is equal to, the square root of 24 breaks down into, what's the perfect square that goes into 24? Square root of 4. And so the square root of 4 becomes 2. There's not a perfect square that goes into 6. So because this is distance on a triangle, we only need the positive part of that. We only need the positive part. B is equal to 2 square root of 6. All right, looking right here. Once again, and I guess I kind of didn't talk about this in the last two examples. You had a large right triangle, and we know that this is the altitude because it goes from the vertex, and it forms a 90-degree angle with the side opposite of the vertex. And so therefore, those three triangles that are formed by that must be similar. So because they're similar, that will allow us to find Z. All right, so let's look here. We have a small triangle, 2.5 on the bottom, and Z as the hypotenuse. Z is the hypotenuse in this one. Okay. Larger triangle here. I'm looking at this triangle right here. The one that has 9 involved in it. This triangle right here. But there's only one measurement of that triangle that I know, and that's 9. What to do? Well, here's the thing, though. Remember that all three of those triangles are similar. So let's look at this large triangle here. There we go. Let's look at that triangle. So if we do like a rotation there, and then like a left to right reflection, This triangle Z then becomes the base, or the bottom of that triangle. And then 9, well, it's not 9, it's 9 and 2.5. That would be the, see, here's the right angle. So 9 and 2.5 make 11.5. That's the hypotenuse. And now we have, there we go. See how that works out when you just do a little thinking. So let's set up our ratios. Hypotenuse of the small triangle over top of the hypotenuse of the large triangle. That's equal to the bottom of the small triangle over top of the bottom of the large triangle. Keep things lined up. That's the large triangle on the bottom, small triangle on top. This is the hypotenuses, and this would be the bottom of the triangles. So everything is lined up here. And let's work some things out. Z times Z is Z squared. What is 11.5 times 2.5? Well, I know 11.5. I know 11.5 times 2 and 11.5 times a half. 11.5 times 2 is going to be, let me just do it for you. I was trying to do it quickly in my head, and I realized that if I were to just do it like this, it would be the same thing. 5 times 5 is 25. 5 times 1 is 5. And 5 times 1. Move over a spot, so you have to add the 0. 2 times 5 is 10. Carry your 1. 2 times 1 is 2, plus the 1. And 2 times 1 is 2. There we go. Add these. We had 1, 2 decimal places. 1, 2 decimal places. And let's finish. Z is equal to, remember it's supposed to be plus or minus, but we're only dealing with the positive here. The square root of 28 and 75/100. Sometimes you can reduce those or simplify those, but I do not believe that you can do that with this one. Any major questions there? There we go. I would like you to try this one on your own. Once again, it's very similar to the last problem. I'd like you to try that one on your own. You hit play on the video when you hit pause, then hit play when you are ready to check your solution. Alright, so I'm looking at a small triangle here. H is the hypotenuse, 6 is the bottom, and then the large triangle, 6 and 15, make 21. The large triangle is already drawn up there for us. Okay, so hypotenuse on the small triangle over top of the hypotenuse on the large triangle. And I always go small to large. Let me mix it up here a little bit just to show you that it can be done differently and you still get the same answer. So hypotenuse on the large triangle's on top, the bottom of the large triangle's on top over there on the second fraction, the second ratio, and 6 is from the small triangle. So now let's go ahead and multiply. 21 times 6 will give us 126. And h times h will give us h squared. We're going to take the square root of both sides. And remember, it's plus or minus, but we're only going to deal with the positive from here on out. So we left with h. Now 126. 126 breaks down into, well, this looks like 12 and 6, right? That's not really going to help us because 12 and 6 really aren't perfect squares. What about 9? 9 is, though. And I know 9 goes into this. So we're going to say 9 times 14. That's 126. The square root of 9 is 3, and the square root of 14 is just 2 times 7, which neither one of those will simplify out. There you go. 3 times the square root of 14. If you can, it's kind of like a little bonus thing. I ask you to work a little bit. Find the length of each, find each diagonal length of the kite. I'm not going to work that out on this video, but if you'd like to try it, bring in your solution. This puts a lot of stuff that we've learned this section and in the previous sections about what you know about a kite, like the diagonals are perpendicular. That's real helpful. So if you'd like to try that, bring it in, share it with me. We'll talk about that. And if not, I think you're missing out then. Either way, I'll see you next time.